welcome to the pump sizing tutorial. We are going to size one, maybe two pumps, see how fast we can get through this, how much tape we have. I think what I thought I'd just quickly show you is the 3D model first. So we had this Google SketchUp model, and I hit File, Preview in Google Earth, so you can do that and pop it up in Google Earth. I'm not sure whether that works on our cluster computers or not, but we also have on the wiki the Google Earth version right here. So if you're wanting to get a little bit of a reference of where things are, it's good to check it out in Google Earth. So James has very kindly built our 3D model here, and so all the equipment that we're interested in is essentially down in here, and we'll probably work with the Google SketchUp model a little bit more because it's labeled a little bit better and it's easier to do measurements and things like that. But you can also do measurements on here. I assume you guys know that you can lay things on and do that and get distances right on Google Earth. That's kind of handy. We have put a kind of a fake version of their stack. Obviously it's not their stack, but it's in roughly the right location. Yeah, there's the stack right there. So it's in roughly the right location. And also I have, I'm probably wrong about this, but I'm guessing that their raw water pumps are either here or here. And I just arbitrarily kind of put our raw water pumps right here. So I'm not sure about that, but it seems like a reasonable place to put them. And so we're going to be interested in how we're going to get our raw water there, and then over to our facility over here. This is the DAF unit, I think, right, James? Yeah. And the ponds are basically here. So there's a little bit of, good thing about Google Earth is there's a little bit of terrain built into the model. So I guess it would be handy if we really wanted to try and get some of the elevations off here, but I'm not sure how to do that. So anyway, let's go and look at the model that we're dealing with here. So we need to pop up the VDI. Okay. And just resize that. So you guys are going to be responsible for these pumps out here. And I'm going to take a stab at this pump right here, which is the water feed pump. So that's what we're going to do first. Whoops. I can get it zoomed in there. So we're going to need to know some flow rates. We need to draw a sketch and all that good stuff. Probably the best thing to do is to actually start with a sketch. And let's do that. This might be a fairly simple and fairly fast pump, I'm not sure. So, let's see, we have our pump here. And since that water is going to be pulling from the lake, essentially what we're going to have to do is put it, it's down, we've decided we're going to put it down by the lake. So it's essentially going to come down into a, I'd say probably it's going to be like a wet well. So there'll be a water level there. And then this will likely have an intake back into Lake Ontario. Now, I haven't done a lot of raw water pumps like this, but I know from past experience there was a big problem with zebra mussels, and so usually what they did is they did a little bit of, I think it was sodium hypochlorite injection back out here, and that eliminated the zebra mussel issues. That might be a bit of a problem with our algae though. So I think we'll have to kind of table that as an issue that needs to be resolved at some point in time, whether we put any sort of zebra mussel treatment facility in here or not. For now, I think we can just basically deal with the fact that we've got a pit that we can draw water out of for the pump. There's actually some good stuff on the internet on pump suctions for these situations. There's a lot of, because the flow rates are high and you don't want to have cavitation and suck stuff up into the pump, they have some really good guidelines around dimensions for pump suctions there. Gould's is a good reference for that. And let's see, I almost need somebody's P&ID here. I'm going to make some educated guesses here. One of them is that there's probably going to be multiple pumps here. So I can imagine there being 2, maybe even 3 pumps providing this service. I'm not going to worry too much about it in terms of the hydraulics. I just need to know it. I just need to know about it. Let's see. Just thinking about this as I go here. Probably strainers and things like that. And we've got our destination really is the Raceway Ponds. So that is, it's going to draw an open pit like that. There's going to be an elevation change. Actually, you know what I'm going to do? I'm going to just draw it a little bit up just so I can kind of show my elevation change a little bit. That's going to be a little tricky to try and get the elevation change out of that. Okay, and there's a whole bunch of other things rolling in here, like ammonia. So, let's see. Essentially, we're just going to dump it right into the ponds, I think. If we don't dump it into the ponds, then what we could do is we could bring it back into the raceway return system, which is near the DAF unit. Let's see. Oh, this is going to get entertaining as it is. Okay, raceway return. And we're probably wanting to bring the ammonia in there as well. So let's bring the ammonia in. I don't think it matters at this point in time where it's coming in. And H3. So you guys would have had to have had some sort of control valve on this. The raceway return is going to, you can't really control the raceway return. That's going to basically be coming back from the DAF unit. So we pretty much have to take, the majority of the water is probably in the raceway return. And then this is really just handling evaporation and losses and stuff like that. So if that's the case, I put the ammonia in the wrong spot. Okay, so the ammonia's got to come in here. Okay. We're trying more of a P&ID than anything else. Okay, so there will be some sort of flow measurement here. I think I saw this on some P&IDs. And essentially what people are doing, I think, is controlling the flow here in order to get a total flow going into the ponds. So so this has probably got an FIC on it. Okay, like that, and an FE. That, DCS like that, and I suspect we either have a total flow measurement here. I guess it could be done like that actually. Maybe that would be the best way to do it. Put a total flow measurement on here, and an FIC like that, and then just put a software signal in there like that, so that we get a total flow measurement. And if this one is low, oh, if that's the case, we don't need this. There we go. We just do it like that. Okay. I still think I'd want to have a flow measurement there. I would totally want a flow measurement there. Okay, I'm changing my mind left, right, and center here. Okay. I want to know how much water I'm pulling out of the lake. So even if I don't control it, I'm going to have a flow indicator there. Okay, that makes sense. So we've got a total flow going into the ponds. It's the raceway return is basically sending us what we need, and in order to make that total flow, we're making it up with that flow valve there, and we're measuring what the total flow is that we're bringing out of the lake. That'll work. Anybody have any other suggestions or thoughts on what their P&IDs look like? Did I miss any features? Would we use multiple injections for the ponds? Yeah, definitely there's multiple injections for the ponds. Yeah, yeah, this is going to however many raceways we have for sure, Josh. Yeah, yeah. So we'll need to think about that. Probably what we could do is, this could become a complicated analysis if we tried to do every single, like analyze the pressure drop between everything, but we could also just look at the furthest place we've got to pump stuff and make sure we can pump the right flow rate up to that raceway. Yep, this could get interesting. And I thought it was going to be simple. I think that's pretty much it. If we need to add to the diagram as we go, that's fine. I guess what we do is this is Lake Ontario. The elevation up to the pump, I don't know. I'm going to say it's probably about 10 feet. We haven't really got a design for this, but it's probably about 10 feet of lift. We might, there are ways actually of building this and having the pump down in a sort of a dry pit here so that you actually don't have to pull out of the, you don't have to pull upwards, you just go straight into the pump. So if we find ourselves getting into problems with NPSH, we may want to rethink that one. And then we're going to want to know the distance from here up to the ponds. And I'm not sure we can pull that out of the model very easily. I'm not sure I'm good enough at Google SketchUp, but basically we may need to bring the water up as far as here. It looks like that's the highest point in the ground. And how good are people with Google Earth in terms of getting elevation? See how low. Says the elevation is 326 feet there. I'm just reading this number down here at the bottom right. 326 there. Whoa! Stop. Darn. Oops. There we go. We're getting warmer. Okay, 326. Let's see if we can get the elevation here. Ah, that's pretty good. 282. This one here is what I'm reading. Oh, you think it's this one here? Yeah, maybe. That one doesn't change. Okay, so wait a sec. Okay, that was, I forgot the numbers. I should have written down. Hang on. That one said 282. What was the other number, you guys? 326. Yeah, I was just trying to put myself right on the surface. Okay, so that says 262. Let's see if we can. Maybe you guys are right. Maybe you just need to click on it. We can get the actual. Oh yeah. Whoa. Stop. $310. Maybe we can rely on that. That might work actually. So that says it's 308. 308 there. Yeah, that looks like it could be. Okay, so 309 there, and 225 at the water. Huh. There, we learned something new about Google Earth. Sweet. Okay, so this is elevation 225 feet. And this was basically 310. That should work. So, really? That's quite a bit of distance, isn't it? Why am I having trouble believing that? There's really that much distance? 306. 236. Oh, wait a minute. That says 254. 241. Oh, wait a minute. There's something. Oh, you know what? It's going right down to the bath. Okay, wait. We want to pick it right there. Yeah. Okay, that's about 263. Yeah, that makes more sense. Okay, so this is 263 on the ground. and the water level is going to be about 10 feet below that. Okay, so that, I'm starting to believe that a little bit more. 40 feet of elevation, yeah, I can believe that, maybe. So this is 253. Okay, do we have, now the other thing we need is, we're going to need some distances and things like that. So my trick for distances and such is to start drawing some, let's see if we can do this fairly quickly here. A little rusty with Google SketchUp here. Okay, so there's our water feed pump there. And we need to run a line, I think we'll probably just try and run the line straight up from the water. So what you need is, the trick here is as you move the cursor around, you're going to get 3 axes that it locks on. The blue is the vertical. The green, I think, is heading north-south. Once you kind of get it locked on the axis, you hold the shift key down and it kind of goes bold there. And then you can basically force, then it'll just stay locked on there. And then you can move out here and you say, well, we think we want to go about as far north as the stack for now. So we'll go right up to the plant. And then we'll pop up vertically. And what we want to do is we may want to move up, say, about 30 or 40 feet. So we're kind of, we have some road clearance. So I'm typing in 40 apostrophe. That gives me 40 feet of elevation. And then I'm going to go red. And what I need to do is I'm holding the center mouse key down and the shift key. That way I can actually move the model around. Okay. I want to be on the red axis to move east-west. Hold the shift key down now that I got locked. And now maybe this would have to run underground. That might actually be something that would have to be done. But the distances will probably be about right. Okay, so I'm going to run to the edge of the stack and then I'm going to drop down to the ground. Down to the ground. Blue. And I went down 40 feet. Like that. Whoa. Whoops, 40 feet. Okay, that gives me that. So I should be basically on ground level, although the ground is sloping up on me. Okay, and hold the shift key down. And I want to basically get onto my pipe bridge here, so we'll run out to about there. Should get me onto the pipe bridge, roughly. Okay. Get the shift key on there. Oh, for some reason I screwed up a little bit there. Okay. And actually, if we ran it all the way underground, there's the DAF building there. Would we tie into the DAF building? No, we basically have to run right all the way up to the ponds, don't we? Okay, so let's zoom out a little bit here. Okay, why don't we run all the way up here? Whoops, green, green, green. There's a green axis there. We'll run all the way up here. And we probably need to run all the way across here. Whoops. We need to run all the way across here too, probably. Okay. Okay, so that's kind of my line length there. And if we want to know how much distance there is there, we can either put some dimensions on it like this. Oops. Come on. There. Okay, got that distance there. And that was going down into where? vertical line there. I know it's 40 feet because I actually typed it in. Come on, you dumb thing. There. Come on. Oh, so close. Oh. There. Okay. And we're done with the water feed pump. Okay, so we just need to add those numbers up to get our line lengths. So we have 344. I just want to write this down here. 344, 12 in vertical, 216. Another 12 meters going down, 274 across. And then 148. And we're going to need to add a little bit of sort of engineering judgment numbers in here. Okay. And we've got basically, there. 2,563, 1055. Okay, who wants to add those up for me? Who's got a calculator? Josh is busy. You want to use sponsored by Hewlett Packard. What'd you get? 602 meters? Okay. We're going to need to add a little bit in there, I'm sure, but so that's our discharge line. So we're good there. This is just going to be fairly short through here. This should go fairly well. Okay. So let's just pop up the wiki and just follow our instructions for doing this. Let's see. Trying to find my instructions. Of course, I can't find them. There we go. Okay, draw a diagram, determine the flow rate. So let's get the flow rate. We need the VDI for the flow rate. And of course, it locked me out. Everybody saw my password there? Good. Okay, so our mass flow rate there is 40,000 kilograms an hour. So number one is the diagram. Number two is what's the flow rate. Okay. That's the nominal flow rate. Now our rules of thumb would tell us that we need to add a little bit to that. So we might want to multiply that by 1.2 is going to be a big number. That'd be a lot to add that to. Our rules of thumb say to multiply 1.2 onto that, right? And then since we have a control valve on here, we want to have a minimum flow bypass. So we probably want to spin that. I'm going to do this the way I think all pumps should be done generally, but I have a feeling that because this is such a big pump and it's such a specialized sort of application, there might be some different rules of thumbs for these for this pump. So I'd want to go back and check some of these little engineering thoughts here. Well, let's do it this way. Okay, so we're going to say this is 15% of the flow. So essentially what we do is divide that by 1 minus 0.15. And that gives us, so Somebody want to check my numbers at the same time? $56,500 kgs an hour. So you remember we said we're kind of justifying this whole idea of a process based on the fact that we have a freely available source of water. So when we go and do the economic analysis, normally what we would do is we have like a cost for various utilities. I think this one we're basically making our own utility. So our cost is having to buy the pump, run the piping, and electricity, and build the facility and stuff like that. We're basically going to include that in our capital estimate and the electricity in our operating cost estimate, and we won't have to actually have a line item in there for the cost of the water, because we basically built it here. Okay, so 56,500 kgs an hour. I'm just going to convert that into US gallons per minute by first multiplying it by 2.2046 to give me it in pounds per hour. So that's 124,500 pounds per hour. And if I divide that 500, that's actually it's not that big a flow rate. It's only 250 US gallons per minute. 249. Oh, that's not that big. Surprised it's that small, actually. Just look like big numbers initially. Okay. So we have our flow rate. Next is to get the inlet pressure. So what we have is we have essentially atmospheric pressure less the line losses here. If you what I did yesterday in class was basically ignore the frictional losses. I think it's pretty close to that. So if we assume the source pressure, that pressure is 0 psig. If we want to size a line and just see how much line losses we might have with, say, 10 or 15 feet of piping, then let's just pop up a there we go. You just click on that and you've got the crane manual, and 250 gallons a minute is going to be down here somewhere. There we go. Let me zoom in here. Maybe. I love how fast this computer is. Here we go. Okay, 250 gallons a minute. This is the velocity, that's the pressure drop. So too high velocity, too high, too high, too high, too high. Getting warmer. We want to be around there. There's 3 feet per second, 0.195 psi per 100 feet. What size line is that? 6-inch line. All this stuff isn't that big at all. I think I'm going to go really conservative because it's a short line, and I'm going to go right to an 8-inch line, not full around. Could do 6-inch, but I'm going to do an 8-inch. And so my pressure drop is 0.061. I lost my line there. Third one down, was it? Second one down. 0.051 psi per 100 feet. PSI per 100 feet times what we think we're going to have in line losses here, or time, number of feet. So let's say we have 10 feet. We're going to multiply that by 4 for elbows and things like that, so 40 feet. So correction for elbows, multiplier for elbows, maybe it's a better way to say that.